Okay, last time we had a long session and we talked about HMM's hidden Markov models. And let me recap the important part that we did, and then we'll solve some questions. So the important part is this. We learned of three things. One is the joint probability question. The second thing that we learned was forward algorithm. And the third thing that we learned was the Viterbi algorithm. Okay, so these are the three key things that we learned last time. Now, going forward, I just want to explain this to you or give you some basic recap of it. So, what is joint probability? So, suppose, let me make it uh, clear by a diagram. So, suppose you have a bunch of hidden states. I'm going to call them hidden states H, and you have a bunch of observables O. So this is hidden state 1, hidden state 2, hidden 3, hidden 4, for example. And then you have observable 1, observable 2, observable 3, observable 4. Okay, actually, let's not do it this way. Let's make the nodes. Let me make this node. This is O1. Let me make this node, call it O2, O3, and O4. So hidden state influences this. What is this called? Emission. What is this called? Jump to the next state. And this, and I have all these things going on right here. So the most simple question could be, you are given a set of observables like O1 to O4, and you are given this and you want to hypothesize maybe state 1 to state 4. Can you figure this out? Well, that's simple that we already did that. This means starting in the state S1. So pi means the starting probability of state S1. Then being in state S1 and emitting O1. So probability of O1 given S1. And then jumping from S1 to S2. Then probability of jumping to S2 from S1. So this is this, and you keep on multiplying other terms, you are going to get the joint probability. Now this assumes that you have some knowledge of the S. S is the state. So this is a very basic question. Now the forward algorithm. Forward algorithm is more interesting because in the forward algorithm, what do is we assume that there is this thing going on, which is this and this going on, hidden, observable, and observable. You have these things going on, this and the classic thing. I mean, it stays the same, the model stays the same. I ask you for this question: what is alpha um, t k? What does that mean? That means at time t, being in state k. That's what this means. Now, so how would you initialize this? That's the easiest one. Alpha 1 state 1, alpha 1 state 2. So this is the time 1, what happens at time 1, and then you can keep on playing this game. Now, why is this important? Is suppose I say, what is the probability of, or how do you compute alpha n step time n 1 alpha n 2? Maybe there are only two states. S state could belong to 1 or 2. That's the only hidden states possible. So you have a bunch of observables like O1, O2, all the way up to On observables, and at the end of this here time n, the system could either be in state 1 or state 2. So what is the probability of the observables like this? Well, you can simply say time n, alpha n, I could be in state 1, or alpha n, I could be in state 2. So that is going to give you the answer right here. So that is the forward algorithm. So forward algorithm means like the probability of being in state 1 when the game ends, probability in state 2. So you can only be in two states according to this right here. Now let me give you a simple version of how this is done. So let's draw a big table like this just for clarity so that we don't have to, do anything else. So this. Now this is state 1, this is state 2. This is observable 1, observable 2, all the way up to observable n. So observable could be whatever, it could be the color red, white, and so on. So whatever is the observable, you can think of it, that is the observable. Now, all that is needed is to fill in this table. So what you need to do is very simply, this is alpha 1. This will also be alpha 1. This will be state 1. This will be state 2. Now, I need to figure out alpha 2, 1. Now, alpha 2, 1 can be written as very simply this. You take this jump plus this jump, add them up. So what is the this jump? Well, this jump is alpha 1 1 multiplied by probability of 1 to 1 jump. Very simple, because this jump will be 1 to 1 jump plus alpha 1. So this is done. We have already taken care of this. Now we're going to take care of this part. This is alpha 1 state 2 multiplied by probability of state 2 to state 1 jump. This is starting, ending. This, and there is something more to it, which is being in state 2, sorry, outputting O2, because this is what is outputted, O2 in stage 1, in S1, because you are in S1 and this. So you have figured out alpha 2, 1. Now, can you figure out alpha 2 time 2 state 2? Well, obviously you have to change very little here. So alpha 1, 1 will be there. Probability of 1 to 2 jump, start, end. Alpha 1, 2, probability of 2 to 2 jump, start, end, 2 to 2. This is here, and this one, probability of outputting O2 from state 2. So you have computed this alpha 2, 1, alpha 2, 2. Similarly, you can go down this thing. So this is an example of dynamic programming, because you fill in the values as you go along and you can be done. So now if the game stops at step 2, so it stops at step 2, so I can say probability of O1 O2. What is the probability of O1 O2? You will say it is simply alpha time 2 1 plus alpha 2 2, and you are giving the probability of the observables, because at the end of time 2 you could either be in this state, you could be in this state, add them up and you get the answer. So this is a key thing that you need to understand. I'm going to put it in red because I need you to really understand this, how to go from 1 to 2. So 1 to 2. So please try to understand this. Make sure you get this whole idea. So are there any questions that we did on this? So let's look at this. I have actually figured out the numerical value, so it's easier for you. This is the answer to the question. Is suppose you have this. So in this case, I'm gonna make a drawing like this. It goes only up to, this is state, and the state could be 0 or 1, two states, and I observe at time 1 A, time 2 B. This is what this means right here. A and B. Now this will be called alpha 1 0. This will be called alpha 1 time 1 and 1. This will be called alpha 2 0. This will be called alpha 2 1. Now obviously what is alpha 1 0? That means the game starts in state 0. And what's the probability of starting in game 0? I think we did this earlier, but just to recap, is 0.3 multiplied by probability of being in state 0 outputting A. State 0A is 0.9, this one. So I can replace this. So this is the answer. I can replace this by 0.27. And similarly alpha 1 1, you can figure that out, and this will be 0.35. Now can you use this to compute alpha 2? Okay, computing alpha 2 is simply alpha 2 state 0 is equal to either this jump or this jump. So let's worry about the top jump first. Let's worry about this. This means 0.27, which is this value, multiplied by probability of 0 to 0 jump, probability of 0 to 0 plus 0.35 multiplied by probability of 1 to 0 jump. This, now this is the jump thing, and the whole thing is multiplied by something which is being in state 0 outputting B. So state 0 outputting B is 0.1. So this thing multiplied by 0.1. So if you think what it is alpha 20 is 0.1, which is this term, multiplied by some terms in brackets. So one term plus two term. First term is this right here. Second term is this. So I have already computed this for you. So zero point 0.1 this multiplied by 0.27 and 0 to 0 jump. So where will you figure 0 to 0 jump? It is here. 0.27 0 to 0 jump. This one. 0.35 1 to 0 jump. 1 to 0 jump. There you go. So I have figured out the numerical value of alpha to 0. Now this is done. We have computed this out. It is something 0 point some 3, 0.038 alpha to 1. Alpha to 0. What will be alpha 2 and 1? Well, that will be prop 0.27 multiplied by probability of jump from what to what? Jump from 0 to 1 plus 0.35 multiplied by probability 1 to 1 jump. And this whole thing has to be multiplied by being in state 1 outputting B. State 1 outputting B is 0.5. Yeah, 0.5. So now you can figure this out, which I have already done for you, which is alpha 2 1. Alpha 2 1 is 0.5, which is this, multiplied by 0.27 into 0.6. 0.6 is 0 to 1 jump. 0 to 1 jump 0.6 plus 0.35 this, and 1 to 1 jump. So 1 to 1 jump is this 0.2. So I have computed alpha this also. So using this numerical thing, I have computed alpha 2 1, and which is this value. So okay, don't worry about the backward probability. We'll just talk about the forward probability. So probability of observable 1 as A, observable 2 as B is alpha 2 0 plus alpha 2 1. And that will give you this term plus this term. And that will be the probability of this. Okay, I hope you get this. Now this is forward probability question which we were able to solve, and it's not very difficult. So here is this thing right here. Yeah, this is what we were working for. Now this is called the forward algorithm. Forward algorithm, as I said, gives you the probability of observables O1, O2, OT. Sometimes this works, sometimes. Okay. So what I wanted to say was um, O1 to OT, and this is an order set. I can compute this by forward algorithm. Forward algorithm has the alphas to work with. The last algorithm, which is the third one, is called the Viterbi algorithm. So what is the Viterbi algorithm? Well, Viterbi algorithm is this. You are given observables O1, O2 up to OT. I want to figure out, so predict this. So this is given, observables are always given. Predict S1, S2 up to S3. That is called the Viterbi algorithm. So figure out the best state predictions. So what happens here is, suppose there are two states. I'm going to make a big table. So state 1, state 2. This, and this is observable 1 at time 1. So I'm going to call this V11. What does that mean? Simply take alpha, replace alpha by V. So this is V12, and this is V time 2 state 1 V2 2. So it should be very obvious because all we are doing is V time t state 1 V time t state 2. So this is what we have. Now the way you compute Viterbi is this. So you can say Viterbi 2 1, it is maximum of two things. It's not like the addition. It is maximum of V11 multiplied by probability of 1 to 1 jump, 1 to 1 jump, or probability of 1 2, which is which of these jumps is more likely. V12 multiplied by probability of 2 to 1 jump. Maximum of this multiplied by probability of outputting O2 given state S1, and that is the value of V21. Similarly, what will be V22? Well, pretty obvious, max of V11 multiplied by probability of 1 to 2 jump, V12 probability of 2 to 2 jump. So this has been replaced by 2 and multiplied by probability of O2 in state S2. So that is the only difference between Viterbi and the forward algorithm. So you fill in these values and you compute all the way up to end. In the end, what do you do? Well, the last step is you take the max of this, and then whichever is max, you trace back the steps. Trace back the steps till the beginning. That is the Viterbi algorithm, and when you trace back your steps, it will give you the most likely value at each stage or each timestamp. Let's go ahead and look at an example of this question. Let's go ahead and look here. Let's look at this one. Maybe this is an interesting one. So you have this data which is given to you, and I need to fill in this Viterbi table. So what are you going to do is I'm going to draw, since there are two states, this, observations for 3 days are this. So I'm going to make a very big table, and there are 3 days, 1, 2, 3. There are two states, healthy, feverish. Time 1 normal, time 2 cold, time 3 dizzy. So what would you call this value? Well, according to my definition, I will call V1H, V1F, V2H, V2F, V3H, V3F. That is what I would compute. Now let's compute V1 healthy, which is probability of starting in the healthy state, which is 60%. Then probability in the healthy state outputting normal. Healthy, so this is emission probability, healthy and normal, zero point 0.5. So, and then let's compute time 1 step fever, which is 4.4. Then fever and normal. Fever and normal is 0.1. So these are the values for time step 1. And if you look at it, I've already computed these for you. So this is 0.3 multiplied at this and 0.04 here. So V1 has been computed. Now V2 time 2 healthy will be maximum of two things. Maximum of, so we already know this. So it will be maximum of V1 time 1 healthy multiplied by probability of healthy to healthy jump. V1 fever and then probability of fever to healthy jump. This multiplied by probability of outputting, so this is healthy, probability of outputting cold in the healthy state. Okay, that's what it would mean. Now, let's say what is max of two terms. So this means 0.30 multiplied by healthy to healthy jump. So if you look at transition healthy to healthy, it's 0.7. And then the second term will be 0.04 multiplied by fever to healthy jump. So fever to healthy jump is 0.4. So which one do you think is larger? Well, my claim is the top one is larger. So I'm gonna say this. So there is no question of this. This is larger multiplied by probability of healthy emitting cold. Healthy emitting cold, zero point 0.4. And what you look at it here is there are three terms multiplied, 21 84 if I'm not wrong. Okay, so this would be the answer, which is here, right here. Similarly, you compute by the same logic, the same rules, compute the time to feverish. So time to feverish. That will take you, like you can take max of two terms, V time 1 healthy, probability of healthy to feverish. V time 1 feverish, probability of fever to fever. Take this multiplied by probability of being in the fever state and emitting cold. Cold in the fever state. And you figure that out and you would get this value right here. And you can go ahead and substitute numerical values and get the answer. So it should be very easy to compute this. Now you are done with step 2. Let's go to step 3. So luckily you only have to go back one step. So V3 healthy, that will be max of two terms, max of V, so this is 3, you need to go to V2 healthy multiplied by probability of healthy, and V2 fever multiplied by probability of fever to healthy. Why? Because I take that back. Sorry, this is healthy to healthy. No, you're right. And this is fever to healthy. This much. Fever to healthy, this multiplied by probability of um, being in the healthy state and emitting dizzy. So probability of dizzy being healthy. If you really wanted to compute it, we could. So we could say, V2H is given to me as 0.084 multiplied by healthy to healthy jump. Healthy to healthy jump is zero point 0.7. And then the second jump will be 0.027 multiplied by fever to healthy jump. Fever to healthy jump is zero point 0.4. This multiplied by probability of healthy dizzy, being in the healthy state and feeling, emission probability. Probability of healthy state emitting dizzy, 0.1. Now, if you really wanted to, you could say, okay, what is this? The numerator will be, I'm just figuring it out here. Um, the numerator will be this, 3 and 4. So this will be the numerator. And the denominator will be, you can figure this term out, 27 into 4, 108. The denominator is 108 and this one. So obviously the numerator, this one is higher. Um, this one is higher. We are talking about this one. So this one is higher and you get just the value. Similarly, you can say V3 fever, compute this V3 fever. And only thing you have to do is probability of healthy to fever and fever to fever. Take this term and then multiply probability of dizzy given fever. So if you do the math at the last end, this is one, this is the other. Check where did you get here. So this is the answer for last time step. How did you get here? Well, I got here from this jump. Okay, so let's trace back to this jump. How did I get here? Well, from this jump. So my prediction is sorry, on the third day it was fever or state 2. The second day it was healthy. First day it was healthy. And that is what is written here, healthy, fever. You can go ahead and practice some more questions from this example set. This is one example. Now there are two states, H state, L state. So the observables are these four observables. First observable is G, G, C, A. So this one will be V1, H, V1, L, and so on. So V1 are very simple. V2, H will be equal to max of two terms. Max of uh, 0.15, which is previous stop, multiplied by probability of healthy to healthy jump. Then it is 0.10 multiplied by probability of, sorry, this is not healthy, it is H. L to H jump, and take the max of this and multiply it by um, H and G. So H and G is 0.3. So this is 0.5, 0.15, which is this one, 0.5, and this one. So I have this answer here, which is here. So I keep on filling these values. This will be V4 times 4 L, V4 times 4 H. Which one is larger? Well, the larger one is the bottom one. This is the top, this is the bottom. Now the bottom is there. Now how do I trace back? Well, it came from the top thing. It came from here. How did I get here? From this place. How did I get here? From this place. So my prediction would be um, H, H, H by trace back. So again, there are a lot of things that you can do and play around with that. For this topic, I would highly encourage you to understand the forward algorithm and the Viterbi algorithm. I would highly encourage you to practice these two areas clearly. And I'm going to stop now. There is, I guess, one more topic left, and then we will be good to go.